Yes. Okay, our second speaker for this session is James Thompson from the University of Colorado Boulder and also JILA. And he's going to talk about photon-mediated interactions for quantum simulation and sensing. Please take it ahead.
This is not on, is it?
No, not yet.
Let's try it now. Can you hear me now? Excellent. So thank you to the organizers. This has been fantastic to have sort of a focused conference, to hear all these great ideas. It's a real pleasure to be here. So I'll jump right in. I'm going to tell you about stuff we're doing in my lab at JILA in the Department of Physics at the University of Colorado. It's going to be in the general theme area that Monica just talked about, so it was a wonderful introduction. We'll think about things and sort of the things we're sort of focused on a little bit differently, but there's a lot of overlap between the two. So if you come visit the lab, you'll see that we actually currently have 4 different cavity QED systems going. One, a standing wave cavity with strontium, a ring cavity with strontium, a standing wave cavity with rubidium that we actually often make look like a ring cavity using a trick. And one that I haven't talked a lot about at conferences is a rubidium thermal beam source, and I'm going to tell you a little bit about that as well. Before I do, we're in the process of spawning experiment number 5 in cavity QED. Here's kind of just the highlights of it. This is in collaboration with my colleague, JILA fellow Shuo Sun. It was actually inspired by conversations with Juan Muniz when he was a postdoc in my group many years ago. And the basic idea is let's do cavity QED at 2.9 microns in this system. And what's magic is that, well, there's going to be a magic tweezer that basically says that we can trap the atoms without perturbing the cavity QED transition we want to use. But it's using strontium. So here's the energy level diagram of strontium over here. And for the bosonic isotope 88 strontium, it has 0 nuclear spin. So you can ignore all the sort of hyperfine structure over here. But essentially, there's a metastable excited state triplet P2. It can connect to a 3D3 state. So you have a pure cycling transition if you really want it, with a radiative decay line width of 60 kilohertz over here. So you plug in numbers, and really because the sort of light or the wavelength you're going to trap at is much smaller than the wavelength you're going to do your cavity QED at. It really sort of softens a lot of the requirements in the system. We think this is super exciting. You plug in numbers, until you do it, who knows? 100 it seems like a slam dunk. 10 to the 5 seems reasonable for C. The real number is actually about 10 to the 6, but I'm embarrassed to write that down. So I will say it out loud and assume no one's recording me. But those are the kinds of numbers, and this would be a whole new regime. I think there's actually a nice analogy to what Monica was talking about. Going to the microwave regime, you in some sense are taking advantage of the fact that sort of the C goes like lambda squared. I mean, I don't think that's all the physics, but I think that's a lot of it. And so really, it sounds silly, but really just going up in wavelength in a way that's manageable, and you think you can handle the technology, we think is interesting. So we think this is going to be fun. We're just getting going. We've already had some theory thoughts about the fact that in this regime, you can actually start having direct dipole-dipole interactions. You can think about sort of spatially structured arrays, all kinds of stuff in addition to this. Okay. So that's just that's sort of an advertisement for something we're starting up. So first talk I want to tell you about is this compact source of non-classical light. And what we're really taking advantage of is that there was this rubidium thermal beam source that was developed in John Kitching's group at NIST up the road. And the idea is that you have some silicon device with some glass on it, and you can etch into it these 100 micron channels that create a very collimated beam of rubidium atoms. Okay, and the idea is to do sort of old school cavity QED. Let's take this rubidium beam, send it through a small gapped optical cavity here. The cooperativity is going to be maybe of order 10-ish. It's kind of the scale. And let's see if we can sort of make these two systems compatible with each other. Does something go wrong when we put these two together? So this is really being led by, primarily Braden Hagen here, and Andres has sort of been, on the device fabrication a little more recently. Where this is going, I'm going to show you some of the results of generating non-classical light in this first prototype. Where this is going, I'll tell you a little bit at the end, is sort of very compact, sort of integrated devices that you might be able to distribute. So here's just a first example. We send light, rubidium atoms, the little blue things here, through the cavity. And then we excite the atoms from the side as they pass through. Because of detector dead time, we actually measure G2s using 2 detectors over here, but we can look at the G2 of tau over here. Okay, so the characteristic feature here is, running from about -200 to 200, maybe -150 to 150. I want to point out the blue is a Monte Carlo wave function simulation of what we expect, including all the trajectories through the cavity. If the atoms were not saturable, that's the red dashed line. Think of if the atoms were basically little mirrors that don't saturate, that'd be the red dashed line. The black is data. Now, I've taken G2 data with cold atom systems before, and when my students showed me this, I was a little bit shocked. The data rate is just so high. The noise is so low. It was really shocking to me when I saw this. I was like, well, be sure to put the data on there. And they were like, James, that is the data. I was like, oh, okay, great. So there's something to be said for running experiments that are really continuous, which is not really where we've been in the cold atom world for quite some time. There are some drawbacks. I'm not going to sugarcoat it. There's lots of reasons people do cold atoms, we trap, and we do that hard work. But this was actually pretty impressive. So it's non-classical if you see that G2 of 0 is less than G2 at some later time tau, and so this is already a non-classical light source. What sets the width of this feature that you see there's a bunching signal? It's just the finite transit time of the atoms through the cavity because they have some velocity. It's the time they spend in the cavity. The data rate is so high, we actually detect about 10 to the 5 counts per second. If we could get rid of quantum efficiency issues, we infer that that's about 10 to the 6 per second in terms of clicks that we should be generating on our detector. So we can actually, because of that, we can go and measure third-order correlation function. So for instance, here's sort of a third-order correlation function, a simulation for comparison. You can take various cuts to this data, and you get sort of stuff that looks like the G2 of tau over here. Okay. We can also say, well, look, if you wanted to trap a single atom and create non-classical light, you wouldn't record in your data set if you didn't have an atom in your tweezer. Okay. So in some sense, you're always post-selecting on whether or not you have an atom present. It's just a question of how often you have to do it. Okay. So what you can think of it as, the first time we get a click on our detector, we can say, we now have an atom inside of our detector, inside of our experimental apparatus. Let's actually measure the G2 of the light right now. Okay. And so this is actually a heralded sub-Poissonian light source where it's kind of like at t equals 0 here. That's when we detected the first click that tells us an atom is inside the cavity. And then you can see that actually we drop below 1 over here in this region. So it's really sub-Poissonian at some later time. And here's a cut through, I think it's this diagonal. You can see it dips below 1. Okay, so this source seems to work. We were able to run it for a long amount of time, and we didn't see a degradation of the cavity mirrors. Everything looks good to go. However, I want to emphasize that here was our optical cavity. Here was the beam source. Here's the big old Kimball physics kind of vacuum chamber. And what we're working on right now is actually saying, let's use the techniques that John Kitchie and his group developed. For instance, symmetricon cells, portable atomic clocks that are in sort of base stations for cell towers and things like this. Let's use all those tools to see if we can make a miniaturized system. So these we've actually manufactured. I have one. If you're curious, I can show you. I brought it with me. But the basic idea is, sort of these little rubidium dispenser pills. You heat them up, you get a sort of vapor of rubidium over here. There are 100-micron channels that collimate the beam. There's a sort of a cleanup region where you sort of pump away rubidium vapor using graphite rods. They're great for pumping away rubidium. And then you have another collimation tubes, and then the cavity is looking in and out. Everything's going to be inside of this completely sealed device. That's the idea, if it works. And the way we're going to tune the cavity length is we just put a piezo on the outside and we squeeze it. We squeeze the glass. That gives us the tuning range. Okay, so that's what we're building up to on that. Sort of a, non-classical light for the masses. That's kind of the, like, does it work? It's a different kind of experiment that I'm used to doing, but it's actually been fun. Okay, let's see. So clearly I didn't highlight the right thing here. Actually, 3 other topics I'd like to talk about. One is the observation of CW lasing between momentum states. And throughout, I just really want to acknowledge the students and postdocs who make this work and collaborators. So you'll see throughout the talk them appearing. I'm not going to talk about this one first. I'm going to actually talk about this one. Okay. I always like to say, you go to a conference, you kind of get saturated. So let's do something simple that we all know about. I take a collection of atoms. I can describe them on a block sphere. Apparently the block sphere is not showing up on this projector. You know, if I put all the atoms in the excited state, the block vector points up, that's the blue over here. We shine a laser on those atoms, we can describe the subsequent dynamics as the fictitious magnetic field that torques the sort of angular momentum associated with that collection of atoms. So it has some J dot B interaction. And essentially, what we get is Robbie flopping, okay? Good, that's pretty simple, right? We all know that. Let's imagine that instead what happens is I don't shine a laser on, but I put a lot of atoms in the excited state. In this case, this is going to be a millihertz line with transition in strontium. It's a clock transition, okay? Radiative lifetimes of 100-second kind of scale. Put all the atoms up there, and the basic idea is a little bit of spontaneous emission goes into the cavity. And when it does, it kind of kicks the collective block vector away from the North Pole, and now it has a collective dipole moment. That dipole moment actually radiates into the cavity, but it doesn't go away, it sticks around, and it sort of torques the block vector more. Essentially, it sort of sees its own self-radiated field, and when you work out all the phase shifts, it turns out that the orientation of that magnetic field is always perpendicular to the dipole moment, or the projection of the block vector onto the equatorial plane, which will be the green here. So when we do this, this is what you see happens. You get it kicked away from the equator, the dipole moment grows, the radiated field grows, but it's a heavily damped cavity, so you don't reabsorb the photons. It's like a self-induced pi pulse, okay? That's one way to think about what the superradiance is. It's initiated by vacuum, is what kicks it off, okay? So this is what you expect to see in the output power over here. Here's what we saw in the experiments in 2016. And so this is at different total atom numbers. This is, I don't know, 200,000 atoms that we're using. You see nothing, nothing, nothing. This is very non-exponential decay. It grows and then it decays over here, and that's the superradiant pulse of light. Why are we doing this on the millihertz transition? Are we just sadistic? Why are we making our lives hard? Well, the reason for that is it turns out that we'd like to build ultra narrow line with lasers and even frequency references. So for instance, by actually doing heterodyne detection of the frequency of these pulses of light, we get 1 pulse per second, we throw the atoms away, we load some more, we get a pulse, throw it away. When we did that, this is already the best active atomic clock that's ever been realized, okay? And so what we'd really like to do is go from this pulse mode, where your Fourier transform limited and you're splitting the line to get the frequency using the number of photons you collect, we'd actually like to go to CW. Okay, so if we go to CW, here's the group of folks who are working towards that. Our long-term goal here is to get a fractional frequency uncertainty of 10 to the minus 18 at 1 second. It turns out that's a really good number, and it is a number that involves having measurement bandwidth. One thing that's very important is if you want to use these things for different applications, you'd like to not only get to a certain precision, but you don't want to get to that precision after integrating down for 2 days. Okay, this is at 1 second. If you could do that, you could start resolving general relativity at sort of the centimeter scale in 1 second. It's about the GR shift. Okay, all kinds of applications for geodesy, gravitational waves, dark matter. So you might think on the next slide, I'm going to tell you how we've achieved this. I'm not. I'm going to tell you something that we saw that was weird along the way. Okay, that doesn't involve lazy on this millihertz transition, but in the process of going to this continuous lazy. Okay. So in order to make this go, we need to continuously load atoms into a ring cavity. You may not be able to see it, that little blue glowy thing right there, that's atoms loaded into an intercavity lattice. That's a magic wavelength lattice for strontium. We basically have a Zeeman slower and a series of 2D mots and molasses over here that sort of load into the lattice, right? One of the reasons we want a ring cavity is we'd like to load atoms into this region with laser cooling beams and then transport them in a moving conveyor belt inside the cavity into this lasing regime where they don't see lasers, and therefore the transition frequency isn't being perturbed or broadened. Okay, so here's just some examples of some camera images where we do the transport over here. But as we're doing this, we're loading atoms into the cavity, and we noticed that suddenly we had a lot of light coming out of the cavity. By a lot, you're totally fine to look into this laser. We're talking about picowatts, okay? It's not going to blind you. But we saw a lot of light coming out of the cavity, and it actually lasts a long time. Here's 30 minutes trace of the output power from this object. I think our record was pushing 10 hours, okay? It just sat there and we were getting light out. There are a couple of things where you can be conspiratorial and say, well, this is just like, it's not like a lazy mechanism. It's just like single particle scattering into the cavity. It turns out that we can, for instance, measure threshold behavior for this light emission versus atom number. We can measure the G2 function, which means it's not just incoherent scattering into the cavity. And we can also see that there's line width narrowing relative to, say, the Doppler broadening of the system. Okay, so it's less than the cavity line width, which is about 40 kilohertz in this system. Okay, so it really seems like laser light, and we were a little bit confused. How can it be laser light? And let me tell you why. There really is a single ground state. It's an m equals 0. I don't know why the minus sign is there. An m equals 0 state. So there's a single ground state in this atom. We have laser cooling beams on that are detuned from resonance. You should think of it as there's no way I have inversion between here and here. This is a 7.5 kilohertz line width transition in strontium. But somehow it seems like these laser cooling beams are inducing lasing. And what we kind of traced it down to is we think that what's going on is we have inversion in momentum space. And the basic idea is if you look at the probability of finding an atom at a given momentum in a 1D distribution, you'll notice that there are more atoms at this momentum than this momentum. And so you can have a process where you absorb and get a momentum kick from the laser cooling beam, and you emit a photon into the cavity that takes you from this momentum state to that momentum state. And because there's a difference in population, there's inversion, and you get gain. You get lasing in the system. Okay. Sometimes in free space, I think it was Hemmerich who saw this a long time ago. It's called a recoil-induced resonance gain. He was doing sort of free space probing of ensembles. Okay. If you take this, basically you can find out that the gain curve as a function of frequency is basically the derivative of this sort of Gaussian over here. Good. So one of the things I don't want to go into a lot of detail, but I want to tell you what was kind of fascinating to us is if we scan the bare cavity resonance frequency by changing the voltage on the piezo, we would see that the lasing frequency, this is changing by many megahertz, is not changing hardly at all, maybe 100 kilohertz. Why is it that the lasing frequency isn't changing when we change the cavity resonance frequency? And it turned out that we measured the number of atoms as a function of the cavity resonance frequency over here. And we did that in something that looks like an avoided crossing over here. But what happens is we scan the bare cavity resonance frequency when the lasing is happening, and you notice that actually sort of the dress cavity mode, this is the vacuum Rabi splitting. These are dress cavity modes we're lasing into, actually becomes clamped. It's no longer changing in frequency. And we're lasing into that mode. And so we had to build a phenomenological model that basically said the lasing process itself, which is kicking atoms to higher momentum, also leads to atom loss. And the system finds an equilibrium point in which it throws away atoms until it actually sort of gets to an equilibrium condition where it can actually be above threshold and lase. It's a really, really complicated mechanism. And so you actually end up with these stable and unstable points of lasing. You predict hysteresis from this model, and that's exactly what we see in the experiment.
I just ask us how to do this. You're continuously loading?
This is all continuously loading, yeah. So we're always putting fresh, so if we lose some atoms, we're always replenishing them, and there's some rate equations of like, what's the rate we're putting them in, and somehow in a way that depends on the intensity, we're also inducing loss.
You say it's super complicated, but it sounds like you're flowing atoms in, there's a loss process, and how is it?
Yeah, it's one of those things of, it's easy once you know the answer. It's one of those things, at first you're like, what's going on? Why? In particular, this behavior that the frequency of the laser did not change when we changed the bare cavity frequency was very confusing to us because we thought we were in a different regime of lasing than it turned out to be. Okay. I won't go into it for the sake of time, but really this is a ring cavity, so we can look at lasing in both directions, and we can actually break the symmetry using between the clockwise and counterclockwise mode by using our conveyor belt to actually transport the atoms as a function of time. And if we're at zero transport velocity, actually the two directions appear to be phase locked to each other. They're lasing with the same phase. But as we increase this, eventually they unlock from each other. This is a little bit reminiscent of what happens in like ring laser gyros as well. So, but the exact mechanism here, we're not sure. Okay. With that, I'm going to draw to the next topic, which is the observation of a driven dissipative superradiant transition. Okay, so you said I told you some trivial stuff about superradiants at the beginning. Why did I do that? Well, this topic is really about making these two pictures compete against each other. What if we have an external drive and we have superradiants at the same time? Can we make them fight each other? And what happens when we do? There go the various animations, great. Cool. So in fact, this idea was put forth by Carmichael in about 1980, that you could have sort of a transverse field plus collective dissipation described by collective raising and lowering operators over here. Antoine Broets actually saw this in a free space experiment and sort of published something in 2023. But subsequent analysis really said you have to account for propagation effects through this free space cloud. It's really not the transition. It's not this model. And so we thought we could do a very clean implementation of that in our experiment using the 7.5 kilohertz transition in strontium. So think of it as a two-level system. We put the cavity exactly on resonance, and we drive the cavity, okay? And the whole idea is that you have sort of, collective cavity atom coupling over here. You have a field drive, and then the cavity is damped. And so you assume that the cavity decay is very large, and so you can adiabacically eliminate the cavity mode. You find that it has two contributions: one, the self-radiated field from the atoms, and the other one, the external drive that you're applying. That's what you get from this. And so you can write down a master equation, and this is exactly the sort of model of Carmichael in this limit. Let's give a pictorial view of this. You should think of it as I have a block vector over here, which will be the green. And there are two components, the field inside the cavity, that have rotation axes, which are in opposite directions. It has to do with the fact that this J minus is a complex number. So in fact, these have opposite signs to each other. Okay, so now we're going to take a cut through the, only look in sort of the two-dimensional plane, which is sort of this cut here. You should think of it as I turn on my drive, that's the red, it's going to want to rotate the block vector away from the south pole. But as I do, I develop some optical dipole moment that radiates field into the cavity, and therefore I have some field that wants to push me back towards the south pole. And if I continue to change the polar angle of my block vector, eventually I'll come to a point where the radiated field and the applied drive actually cancel each other, and you get a steady state over here. So if you work that out, you can say, well, what would steady state, be? You can sort of rewrite it in terms of the drive and C times gamma, the radiative line width of the excited state. And essentially, you should go through a transition where you can no longer balance the applied drive versus the self-radiated field when the block vector gets to the equator, because that's the biggest radiated field it can ever have. And if you ever go past that, then you can never cancel. Okay, and so what happens is you get a transition where past this point, you just start Rabi flopping. Okay. And so below this point, if we take the sort of expectation value or the time average value of the spin projection JZ versus the drive, the external drive we apply, you see that it sort of comes up from the equator, but then sort of stays there. It doesn't go any further until you hit the equator, and then you go into something called the normal phase over here, which is just single particle Rabi flopping. Okay, so we can actually see that in our experiments. We trap the atoms, they start in the ground state, we turn on this external drive, we hold for about 10 microseconds, then we measure the spin projection JZ, and we can do it for different atom numbers. That's the different colors here. And we looked at this spin projection. What you see is actually it comes away from the south pole in the steady state, and they eventually makes a transition into the normal phase and Rabi flops. If I renormalize by sort of this NC gamma over here for the different atom numbers, you see they collapse on each other. You don't see that it becomes flat on this side. You can ask me about that, but it has to do with the fact that the way we freeze the dynamics is by optically shelving the atoms in triplet P1 into some other metastable states. And it's just not quite fast enough to get a very, very clean separation of timescales. Cool. There's other stuff we can measure. I'm going to skip through it. Where could we go with this? So we've seen this transition. We were interested in what could you do with it. One possibility is we could actually create entanglement for matter wave interferometers and clocks. And the basic idea, it's a little complicated to explain. I'll refer you to here. But the basic idea is you use this, this steady state in order to sort of generate a Berry phase in the system that essentially reproduces a one-axis twisting style Hamiltonian. Okay. The other idea is in the context of a superradiant laser is that most of the light that sort of leaks out of the cavity when you're building a superradiant laser is kind of wasted light. You're going to do homodyne detection of the light coming out of the cavity relative to a pre-stabilized reference laser. And if the phases are aligned, then the signal on your homodyne detector is 0. So you really didn't need any light coming out at all at that point. And so there's a way that we can actually, we think we could apply feedback and essentially put the sort of superradiant block vector kind of in the dark. And by doing that, we reduce sort of recoil heating associated with every time we get a photon out, we're going to have photon recoil heating, which is a big problem. Okay. So the last topic, which is going to be the broadest, is cavity-mediated interactions and gap protection. All right. So I'm here to wave the flag that Monica did, which is that it turns out these cavities are pretty darn good at generating entanglement, okay? And entanglement as a resource for quantum sensors. And so here is on a log scale, the directly observed enhancement over the standard quantum limit in phase resolution versus year. And all the sort of solid points are sort of R community, okay? And you can see the other platforms over here. About state of the art is 18 to 19 dB of improvement using QND measurements with rubidium in Mark's group and in our group, okay? I'm going to just briefly tell you about 2 points we've added here, which are now trying to push these kinds of enhancements into quantum sensors. The first one, we took the techniques we developed in my lab down to Jun Yi's lab, and we were able to use what are called quantum non-demolition measurements to create a squeezed atomic ensemble here, transport another subensemble into the cavity, create a squeezed subensemble, and run a differential clock measurement over here. One of the things I think is very, very important is to figure out how to get these kind of differential measurements to extend well out beyond the phase coherence time of the local oscillator. And so we've actually thought about this. We've come up with this in-atom decoherence-free subspace, which makes you completely immune to the local oscillator noise. We think that's super important. Is it trivial to make? No. But on the other hand, we think this is where we need to go. Okay. The other type of sensor is something called a matter wave interferometer. Hopefully everyone knows what a matter wave interferometer, but let me remind you, if I prepare some atoms at a given momentum state, I can get the atom to non-resonantly go through some excited state up here, I'm not drawing, absorb a photon, and then emit a photon, stimulate down. And in that process, I can change the spin state, but I also can absorb momentum and get momentum kicks, okay? And so we do this in our rubidium system. We let the atoms fall along the cavity axis, and we drive all these lasers that will give momentum kicks along the cavity axis. And so for instance, we can drive this kind of Raman momentum transfer where we start in one momentum state, we do a pi/2 pulse, and then we do another pi pulse down to the same spin state. You can see we have these 2 peaks in velocimetry, showing that we've created these 2 momentum states, okay? We can also do this with Bragg pulses where you don't change the internal spin state, you just change the momentum state. And so for instance, here are velocimetry curves where essentially we do a pi/2 and then a series of pi pulses along the cavity axis. And once you've done this, you can actually put all this together to realize a matter wave interferometer. These are like pi/2 pulses, pi pulses, all the normal things you would do in Ramsey. But now here you're manipulating momentum states rather than spin states. Okay. And so this was done, these are very difficult experiments where you run a mini matter wave interferometer, and we use both QND or one-axis twisting. We can talk about that later, to generate an entangled state, injected to the interferometer and see an enhancement at the output of the interferometer. Okay. And then there was also a recent result using cold collisions between atoms in Karsten Klimt's group here in 2025. So we're manipulating momentum states, and one of the things we wanted to ask is what other kinds of things could we generate? And Monica talked about it. It's going to be sort of a momentum version of spin exchange. So we call it momentum exchange interaction. So imagine I had atoms in P naught plus H bar K. We're going to let them fall along the cavity. That's the P naught. And then minus H bar K. You could have a process where we inject a dressing laser into the cavity. An atom in this state absorbs and emits into the cavity. But before that photon has a chance to escape, the red atom could absorb it and stimulate to the ground state. The red and blue balls have exchanged their states. And if I think of this as a pseudo spin half, then I can really just map this onto sort of an all-to-all J plus J minus exchange interaction. Okay. And so this was done in the context of spin degrees of freedom. In fact, we heard about it in the earlier talk from Monica, beautiful work. And there's also recent work with both spin and momentum involved from Tillman's group as well. Okay. Good. So if I take this spin exchange, it does many things, but I'm going to focus on one of the terms. If I take J plus J minus, I can approximately rewrite this as total J squared minus JZ squared. okay? There's a single particle term we're ignoring, okay? But when we do that, you can ask, what the heck is that one? What does that one do for you? It's a weird one, okay? And so to look for it, what we do is we run an interferometer sequence where we hit the system with a pi/2 Bragg pulse to put ourselves in a superposition of different momentum states. And then we wait some amount of time and we do another pi/2 pulse. We vary the phase of that final pi/2 pulse. And we look at the amplitude of the fringe as a function of delay time between the pi/2 pulses. So you just think this is like the coherence or the contrast in the interferometer. In the black points, you see they fall off, okay? This is basically, you have a wave packet and it's separating as a function of time. And when the wave packets no longer overlap, you lose your coherence, you lose your interference, okay? When we turn on the interactions, we have this total J² term, which says that in some sense, it suppresses single particle dephasing. It actually suppresses this recoil. And that's evidenced by the fact that the contrast remains high for much longer, okay? Let me see, the animation ran over here of the wave packets. Let me go back and go forward one. With no interactions, the wave packets separate, but with the interactions on in the simulation, you see that actually they don't separate, even though it's in a superposition of different momentum states. Okay. Good. So what I'm telling you is here's a Gedanken experiment. If I have n atoms over here and I have no interactions on, if I have a single photon gun, I shoot it into this cloud of atoms and it gets absorbed, some later time, one atom will come out with velocity h bar k over m. Okay, just conservation of momentum. If I turn on this momentum exchange interactions, what I'm telling you is that the whole cloud actually absorbs that momentum. It recoils as a single unit. This is really like a completely different, it has like lots of analogs, and yet it's its own beast. But it's very similar to Mossbauer-Lambdicki spectroscopy, which really is at the heart of all of our sort of precision measurements that we do, especially with atomic clocks. Okay. I'll point you to a theory proposal where we also think we know how to extend this kind of interaction to also build solitons that also suppress wave packet spreading, in addition to binding the momentum states together. Okay. So that's nice. Some clever matter wave interferometer thing, but maybe you like clocks. At least where I'm around, people like clocks a lot. They say, well, that's a nice story, James. But we said, look, no, this is real. You could really use this to suppress dephasing on a clock transition. So we have this ring cavity, we can load an ensemble, and we can actually hit it with a pulse of light that places atoms in superposition of triplet P1 and singlet S0. And then we know the Doppler broadening, and we should say that we should lose the coherence between this state and that state on a time scale shown here. Just think of it as coherence on the vertical, time over here, okay? But when we actually have this cavity present, we see that actually this is data. It's smooth, but that's data when we turn on the interaction. So we're actually getting this kind of protection of the optical coherence on this optical transition as well, okay? And you can read about that over here. Luckily, I don't have to talk about everything today because Eric is here, standing in the back. He has a poster and he can tell you all about these experiments. This is actually, this LMG model is related to this self-trapping that I think Monica was talking about, but not in an SSH way. It's sort of more truly a double well kind of potential here, but also sort of physics related to emulating DCS style physics. Okay. I will sort of preview one thing off of this poster, which is we're exploring right now sort of, can we emulate atoms tunneling in a lattice, but using an internal degree of freedom of strontium, because we have a nuclear spin 9/2, and so we can have 10 nuclear spin ground states if we want, and that's like a sort of 10-site lattice. And so can we build an interaction where an atom can only tunnel from here to here if an atom over here tunnels from here to there, okay? And so that seems to be working. We're getting first results on it, but this also, I'll highlight, requires single shot readout of all 10 nuclear spin states, and we figured out how to do that. And so he can tell you about that. Okay. Along the lines of figuring out different kinds of Hamiltonians that we can engineer, I want to tell you about how we can sort of generalize the kinds of interactions from this exchange interaction, which I've already shown you over here, where we apply a dressing laser, detune from resonance with a cavity, and it emits briefly a photon into the cavity and then gets reabsorbed. And the frequency of that photon is shifted by the kinetic energy difference between the two momentum states you're connecting. That's what omega z is here, okay? So that photon goes in before it has a chance to escape, it gets reabsorbed by another atom. That's the exchange interaction. But now if we turn on another pump and we separate it by twice the kinetic energy difference between the momentum states. If we start with two atoms in the same state, we can have a process where the blue atom absorbs, emits a photon into the cavity, but before that photon can escape, the red atom actually absorbs it and stimulates into the cavity. So pairs of atoms have swapped their states. Okay, and by doing this, now we have a term that looks like J plus squared plus J minus squared. But it turns out we can tune these independently of each other because this involves, terms like this involve interactions twice with the same pump or dressing laser. Whereas this term involves one interaction with both of the applied dressing lasers. So we can actually, by changing amplitudes over here, we can actually realize arbitrary all-to-all XYZ Hamiltonians. One of the things we've applied that to, but I won't go into for the sake of time, is we've applied this to something called two-axis counter twisting. And I would call this a magical unicorn, at least for me. I remember seeing this in grad school and being like, well, that'd be really cool. I wonder how you can really do it. And for a long time, we didn't know how. And so the basic idea is in Kitagawa and Ueda, they proposed one-axis twisting, which has been the workhorse of the field for quite some time. It's an all-to-all icing interaction, JZ squared here. But they also proposed in that same paper exactly this Hamiltonian, J plus squared plus J minus squared, and it actually gives you exponentially fast squeezing that in principle can take you to the Heisenberg limit. Okay. So I'm not going to show you the data, but we've actually sort of mapped out flow lines similar to what Monica was talking about on the block sphere to sort of verify that we can generate that. We have two unstable bifurcation points and two stable points in the system. It sort of corresponds to what we want. We had not seen squeezing yet, in part because we're very sensitive in this system to laser phase noise at an offset of about 500 kilohertz from the carrier, and we're going to beat that down and then see if we can see squeezing. Okay. The last thing I want to say is everything that we know how to do in cavity QED has always been two-body interactions. Like whatever the form, JZ squared, JX squared, J plus squared, whatever. If you unpack that, you can see that their atom I and atom J are talking to each other. It's all to all, but they've really sort of interacted in pairs, okay? And so this is a two-body interaction. But what about a three-body interaction or four-body interaction where, for instance, three atoms flip their states at the same time? Can we generate that? And at first, you might imagine that this is going to involve going to the higher and higher order in perturbation theory, and it does. So the chi's are getting smaller. But it turns out because it's all to all, you have to actually account for the relevant energy scale as n chi 2. For this one, it's n squared chi 3, and for this one, it's n cubed chi 4. And n is big, it's 1,000, okay? So even though the chi's are getting smaller, you're going to higher order in n, and it turns out that it's actually competitive. You can actually see this. And so here's just the way you realize it in the experiment. Again, for the sake of time, I'm not going to show you data or anything. I just want to give you the concept. Basically, previously, we would just apply two pumps that are separated by 2 times the kinetic energy difference between the momentum states. We just separate the pumps by 3 times. That's it. And now we have a higher order process where 3 atoms starting in one state, absorb, emit, absorb, stimulate down. And in each of those steps, you get a Doppler shift, or conservation of energy says the frequency of that photon changes in each step. So you absorb from here, you emit to there, this gets absorbed, you emit to there, and then you stimulate it into there. And then you conserve energy, and it becomes a resonant process. Okay. So we can do this for 3-body, but we can also do it for 4-body interactions as well. And so you can look here if you're interested. Okay, I think that's going to be it for today, but I really want to thank all the wonderful grad students and postdocs, as well as collaborators at JILA and other places around the world. With that, I'm happy to take questions.
Thank you very much. Any questions?
Very cool talk. I was curious if your goal is to create a squeezed atom interferometer. Are you better off starting with spin squeezing and then transferring over into momentum states, or using one of these direct momentum-based interaction techniques that you were talking about later?
That's a great question. Actually Monica mentioned it, and I sort of shook my head in the audience when she said it. One of the things that's a little bit unclear when people talk about squeezed states or non-classical states for sensing is that you really can't have a conversation until you tell me the classical constraints on the problem. And so let me give you an example, and then I'll circle back to really answering your question. LIGO is an example about using non-classical light in order to enhance sensitivity. But it turns out they didn't have to. They really didn't. They could have just gotten Congress to give them what, like another $2 billion. And they could have just built one next door. And they would have gotten 3 dB enhancement in sensitivity. Okay. And you go, well, yeah, but come on, like that's not fair. It just turns out until you define the classical constraints, it's hard to tell you when it's going to win and when it's not. Okay. So if you say that my goal is to build a very compact matter wave interferometer where I'm not trying to look for like ultimate sensitivity, but I just want compactness, I think this might be a good way to go. If my goal is I want to sort of build a sort of 100-meter tower or something like this, it may be better to start off in sort of spin squeeze states and then map to momentum. I think it's an open question, but I suspect that may be true. And in particular, I have in mind, I'm not sure if we'll do it or not, but like I'm toying with the idea that if you could really create spin squeezing in the ground state of, say, ytterbium, you have a nice spin half sitting there. You could also do it in strontium. There are tricks for doing this in strontium as well. But you can create spin squeezing, and then essentially you can apply the same AC Stark shift from a laser to both ground spin states. It's very insensitive because it's just pure nuclear spin. So you can imagine that would allow you to create the squeeze state in a cavity where you really want to be tightly confined, so you have good interaction with the cavity, but then still do delta kick cooling, so you'd be able to sort of launch this into a matter wave interferometer. And so I think there might be some interesting things to do there. But if you need to do delta kick cooling, so the cloud doesn't expand during this very long time interferometer, you may need to do it in something like nuclear spin states of something like strontium or ytterbium. Like that's my best thinking at the moment. I'm sorry.
Thing?
Yeah.
Is there a prospect of not having that be a multi-million-dollar machine?
Or for which one?
This continuous, you got a laser that runs for hours. It'd be great to use that to probe a clock or something. Can you?
Yeah. Okay. So we are working towards the idea of getting CW lasing on the actual clock transition. Right now, this is not a frequency reference.
This is the 9 kilohertz one.
It's on the 7.5 kilohertz, but just be clear, the lasing is not between the upper atomic level and the ground state, and therefore it's not an optical frequency reference. All the phase noise on the emitted light just tracks the phase noise of the lasers you're applying. But could we actually realize something in the future? I don't know, man. You're asking for something that gives you 18 digits in 1 second. It's going to be expensive.
Can we negotiate?
What's that?
Can we negotiate?
We can negotiate, but I drive a hard bargain, man. I just think that, like, at least in the first generation, it's going to be sort of complicated. But I really do have a lot of confidence. You hear all the wonderful sort of innovations that are happening even within this conference being shared, that one day these things will just keep getting simpler. I've got to tell a story. When we first started squeezing, like we had to flog the machine to get 3 dB of squeezing. I mean, like we turned every knob, we optimized everything you possibly could. And then the next generation of students came in and we were pushing towards 10 dB for the first time. And I wanted them to sort of, as a function of sort of some knob, sort of look at the amount of squeezing. And basically where they started taking data was like 5 dB of squeezing. And you're like, no, make it worse. And they're like, oh no, it's terrible there. Don't do that. And I'm like, no, it's just what's really hard 5 years ago is easy today. And so I have a lot of confidence in that.
Yeah. 50K?
60 and a hat.
First of all, thanks for a really very nice talk. I wanted to ask about the multi-body interactions. So in particular, so for 2-body, there's this sort of square root of collective cooperativity interaction to decay ratio. How does that go for the multi-body interactions?
Okay, so the answer is we don't know yet. We're actually writing a paper on it, and maybe I won't show anything. That way I can deny later. The theoretical result seems to show that even if you have spin flips with this 3-body interaction, you get a scaling that it goes like n root c instead of square root of nc. Okay, which would already be a pretty big win. In other words, you don't, when you have spin flips, normally you go like 1 over root n improvement relative to the standard quantum limit in noise variance. And it seems like even in the presence of spin flits, it goes like 1/n. So you really, in principle, get Heisenberg scaling out of using the 3-body plus time reversal. And that's one of the tricks. You really have to think the way to read this out. Sorry, Aubrey.
Naively, it feels like a higher order process should be less coherent or something. So, or can you give some intuition for?
I basically, okay, look, this is what they're seeing. And basically I'm in the mode of, I don't believe you. Like, how does that work? I'm asking the question you asked. So I'm kind of in your camp. I'm still poking at it at the moment. I would have thought at least it would be break even. What's different about this higher body interaction is because the chi, that sort of single particle-like interaction, or like 3-body interaction term that just sits out front, that falls off strongly with the detuning from the atomic transition, much faster than we're used to for like Q&D measurements or or one-axis twisting or exchange interactions. So it forces you to work closer to the atomic transition, and it's a question of are we doing all the optimization correctly to get it? So I'll say it's an open question. We have a manuscript, but I'm really poking hard at it because I want to make sure it's right before we publish it. Yeah.
Okay, one last question.
Yeah, I guess related to that, what atom number would you have to hit for these like chi3 or chi4 interactions to not be perturbative anymore?
For them not to. So there's always a requirement in order to think about these cavity-mediated interactions, you have to always be in a limit where you can adiabatically eliminate the cavity. And usually that requires that your detuning from the atomic transition is much larger than something like root n2g, okay? And so basically it's a question of like, how close can you push the interaction, basically move the cavity close to the atomic transition frequency before you start violating this adiabatic elimination. Right now we're doing this with 1,000 atoms is what we're typically operating at. We would run into trouble due to the finite ground state splitting, hyperfine splitting of rubidium. If we scale up to 100,000, like other approximations would start to break down. So I will tell you, I have 2 hats. I have the hat which says I want to make a precision measurement, and I have a hat which is I put on that says I think this is really cool physics. Somewhere I'm a little sort of like I'm not sure which hat to put on in this case, but I think that's a good space to be in, where you think, well, maybe there is some application in precision measurement. But for me at this point, I'm just wild that this works at all. Yeah.
Okay, thank you very much. And it's time for the coffee break now, and then we meet again at 4 p.m.